Hello everyone. In this video, I'm going to explain my homework 4 project. So in this assignment, what we did is like we parallelized our previous homework 1 code using OpenMP. The homework 1 was originally like it's a code that creates a random array and it repeatedly smoothed it to reduce the standard deviation. So for this homework, our goal is to make the computation run in parallel across multiple CPU cores so that hopefully we're gonna observe a speed up. So let's check the code first itself. Vim homework 4 minimum. Let's see. Um, so in here, as you can see, the random array part, it creates a random array. Yeah, this is the main idea of this void, and then the we have the sum parallel one in here. Like sum parallel actually it calculates the mean of the uh, array, and then here it calculates the standard deviation. So it uses the summation of this random array, and it calculates the deviation at here. And at here, like it smooths at here also, like we just talk about the W parameter at homework 1. So what W does is that like it adds the effects of the neighbor cell to the actual cell. So like actually it helps us to smooth more. When you change the W, the smooth operation changes dramatically. We observed that one in homework 1. So in this one, like the idea was adding the OpenMP, like make a parallelization. So as you can see, like from starting with the pragma of parallel, so we parallelize the summation, standard deviation, and smooth operation at here. And lastly, at the main one, we're just printing the first 8 array, and then it just prints the standard deviation, first deviation, second deviation, third deviation after the smooth operation. And hopefully this time we're gonna see the time that we spent for the parallelization too. Let me show. Uh, so let's go out from here. So first, let me execute it. Okay. So right now we have the homework for min, and then let's run this case with using one parallel right now, one CPU. So let's run it. So it says the smooth operation take around 0.0000106 second. So let's run this case with two. So in this time, we get the result a little bit slower with 0.000099. So what I do is most of the time for the scaling analysis, I double the number of processors to see what is the limit, because after certain point, parallelization gonna be meaningless. So this is this place that we should stop. Actually, right now, from one processor to second processor, speed up is pretty less. So I think this code itself is not I don't think it is logical to do parallelization for that code. I think it's kind of meaningless. But if we work maybe a little bit bigger data, then it can be meaningful. But since our case is not that really big, I don't think it is that really logical. But let's run the same case with the 4 processor. Okay, as you can see, after the second processor, we double up the processors, but we didn't observe speed up. So the time that we spend is increased with using 4 processor from 0.000099 to 0.00013. So it is the point. So for this case, sec 2 processor is enough. I think one processor is enough too. So that's since we didn't observe too many big speed up. I think this case is not suitable for parallelization, but this is the way we can observe it. Let's run this case with 8 processor and let's see what's gonna happen. I think based on my knowledge, we should observe time to be a little bit higher than 0.00013. Yeah, 0.00140. Because this parallel, like this scaling analysis kind of gives us like a V-shape graphic. So we reach the minimum with 2 processor, and after 2 processor, it's gonna always increase. So there's no point to like continue this experiment. So this is the end of the video. Thank you.